My name is Mr. Bachumat. My rec number is 223003680. So we are here as group 4, and we are going to be looking at the presentation of today. We have talked about how we can teach electromagnetic induction. So before without delaying, let's dive deep and see what we are going to see today. The topic of today is electromagnetic induction and Faraday's law, and we wish that at the end of this lesson you will be able to explain magnetic flux, the real meaning of magnetic flux. You will be able to know the Faraday's law as well. You will be able to state as well as Lenz's law, and we will talk about the application of electromagnetic induction and Faraday's law. That's where we will come across the hydroelectric power generators. That's where we look at power transformers, and that's where we get the meaning of eddy currents. Okay? So without taking too much time, let's dive deep to the meaning of magnetic flux. We have seen previously in year 2 that maybe what wind or water may be flowing through the tube or a window. So that's the same scenario that we have to think about a magnetic flux. When we say magnetic flux, we are talking about the amount of magnetic field lines that are passing through a given loop. Okay?
Yes.
A given scenario, you can say that, think of it like a wind passing through the window. Okay? So from there we are talking about which volume of the wind that is passing through a given window. So you know mathematically, magnetic flux is equal to the magnetic field strength times the area of the loop times the cosine of the angle theta. And this angle theta is the angle between magnetic field strength and the area vector. Okay? So that's why this magnetic flux will be maximum when magnetic field lines are perpendicular to the loop, and will be 0 or minimum when magnetic field lines are parallel to the loop. Okay?
Yes.
So that's it. So we have also factors affecting magnetic flux. One of it is magnetic field strength. So the magnetic field strength affects magnetic flux in such a way that when you have a big magnet, it creates the magnetic flux, the big magnetic flux. But small magnets create a smaller magnetic flux. Of course, the area of the loop affects the magnitude of magnetic flux, as well as the orientation of magnetic field lines. So let me show you using the simulation I have. So we can look at this one. Let's have bulb there. So we have magnet and we have the loop. Okay? And we will create magnetic flux when I change this magnet to be in the relative motion with this loop. So, but as I increase the area of the loop, you can see. So the magnetic flux that I will be having with a small loop will not be the same as I will be having when I have a bigger loop. Okay? Yes. And if I increase the size of the magnetic flux will increase as well. Okay? Yes. So that's all about magnetic flux. So let me welcome my group member to talk also about, to dive deep about Faraday's.
My name is Rukundo. We've reached number 2213 12 741. We are going to continue to Faraday's law. So, what do you observe here? What do observed a bad magnet.
You observe bad magnet.
Clap for him. Another thing you are observing. Yes, Damo.
I'm observing a bulb and wires.
Okay, thank you. So now we are going to use all this material we have here and try to experiment Faraday's law and by considering the procedure. We are going to move this bad magnet toward or away these loops and also we try to change the strength of the magnet and even the area of the loop. Then after moving this bad magnet, we will record the observation. Let us try to move this bad magnet toward this loop. Try to change even the strength of the magnet here. If you change, if you increase or decrease the strength of the magnet, do it even if we are at 90%. Change also, move the bad magnet. Also, you can try here, while we increase the size of the loop. Also move the bad magnet. Okay, based on your observation, you have seen why we are moving the bad magnet toward or away toward or away the loop, while we are changing the strength of the bad magnet or while we increase or decrease the area of the loop. What have you seen? Based on your observation, can you try to state the Faraday's law? Based on the observation, what you have seen. Yes?
Faraday stated that when a magnetic field is changing with time, it induces electromotive force or current.
Thank you, clap for her. Okay, when we change the magnetic, the rate change of magnetic flux induces electromotive force. Okay, thank you. Who can try to write here a mathematical expression of Faraday's law? Thank you. Let us invite another group members to continue to row.
Hello.
Hi.
My name is Nyasa Fajian with reg number 2230-26749. Now we are going to continue about Lenz's law. Now, based on this material we have here, who can tell me the name of this one? I need the name of this material. Correct? Strong magnet. Thank you very much. Who can tell me the name of this material? Shabaya. Speak loudly. A coil. Good. Now, based on the observation that we are going to make, I need your attention. After the observation, you will tell me what you have observed. Here we have the moving magnet. Also, I ask you to observe what is happening here. Now, based on your observation, tell me how can we state the length is law? Who can state the length law based on the observation? Yes, Yvonne?
Thank you very much. The Lenz's law can state that when a magnetic field is changing with time, it induces the current which is in the opposite direction to the magnetic field that induces it.
Thank you very much. Clap for her. Now, based on this observation, we can state Lenz's law that the induced electromotive force is in opposite direction to the cause. Yes? Now, based also on this Faraday's law, the induced electromotive force is equal to the negative number of turns to the change of magnetic flux with respect to time. These negative indicate the opposite direction of induced EMF and the magnetic flux. Thanks. Let's invite my colleague to continue.
Morning class.
One,
My name is Daniel. My rig number is 22123060. So I'm going to continue with the applications of Faraday's law, Lenz's law, and magnetic flux. We are going to see how can those laws, even magnetic flux, can be applied in our real life situation.
yes.
So I'm going to talk about the one application is called a generator. We are going to see how a generator can use a Faraday law to operate.
Yes.
So we can use a simulation to understand more. So here we have three parts. The part one is a water tap as a source of water. We have a second part with a turbine combined with a strong magnet. We have a coil and a bulb. So on this source of water, there is a source of water which will make a turbine to rotate with a magnet. Then after, there is production of, there is magnetic flux which will provide induces electromotive force inside the coil which will make a bulb to get light. This EMF inside on the coil will provide the current which will make a bulb to produce light. This is understandable.
Yes.
Thank you.
Good afternoon.
Good afternoon.
This I'm going to do with the application of the community. My name is Bruce Aziz. My rig number is 22-300-2297. The other application here is transformer. I think that you have some hint about transformer. Is anyone here who can remind me what is the meaning of transformer? As you have seen in past module and past code electromagnetism. Do you remember that? So anyone who can define the term transformer? Yes, transformer. I choose random. Yes, Shabayo, tell us transformer.
Transformer is an electric device that decreases or increases the voltage.
Repeat again.
It is an electric device
Yes.
that increases or decreases the voltage.
That increase or decrease the voltage. So thank you so much, Shabayo. Anyone with the idea, oppose the Shabayo's idea? Second, is there any idea? Okay.
It is the same thing.
Yes. Another one. Gilbert, what about you?
Yeah, I think as the name suggests, you are understanding that it's transform. It means it transforms. So it can transform in two ways. One increasing or decreasing. So transformer, I think, is a device which transforms voltage or current either by increasing or by decreasing the amount of voltage or current.
Gilbert, thank you. And as you said, a transformer, you can conclude that it is, first of all, a device. That device transforms electric charges between circuits through the process of electromagnetic induction. So we are going to see here the FET. This is a FET simulation, and the transformer consists of two coils. The one is primary, which is this one you can see here, and the other one is this secondary coil. So as we change this coil, you can see that here it lights up. You can see that. So as we are changing the magnetic flux, it uses the EMF, as you can see, and it can give here the energy or the light, as you can see that one. So that is my conclusion. That is, I can conclude that this transformer, nowadays it is used in different applications here outside to create the energy you can use our home. So thank you so much.
Thank you.
Okay. My colleague, and continue where I stopped. Thank you. Welcome, Nadine.
Thank you so much. I'm by the name of Pamela Nadine with registration number 2230-12693. I'm going to continue about another concept which is called eddy current. Eddy current are loops of electric current induced which are formed when there is magnetic field changing. Mean that if you have a magnet and you change it inside the electric current, those loops which are formed, they are what we call eddy currents. Do you understand?
Sure.
Yes, and we can continue about the effects of electric eddy currents. There are many different effects of eddy currents. The first one is about heat. It causes energy loss and heating in the transformers. If there is a changing in magnetic field, of course there is also energy loss. There are some energies which are lost. And also it has effect on detection. They are helpful in metal detection. When they are interacted with some metals, there is also detection of metals. To mean that if they interact with metal, they can also, there is formation of eddy current. And also, let's have short assessment. I want everyone to take a sheet of paper and do this assessment. The first question says that state the Faraday's law and Lenz's law. The second one, explain how generator works using Faraday's law. The third one, explain two applications of Faraday's law. I want everyone to take a piece of paper and do this assessment. Individually, it is not a group work, it is individually. You have only 5 minutes.
Yes.
Do the assessment. Quickly say that.
Yes.
Even if she's a notebook, it's okay. You can give it to me. Finish? So, thank you so much. This is the end of our today's session. Let us meet next time. Thank you.